So, there is a problem set. It is due a week from Wednesday. And then we have a fall break. There will be, I believe, 2 more problem sets after this one. And then we will begin thinking about the final project for the semester. Okay, so basically there'll be a month before to do the final project, plus the time over finals week, which we won't have a final. All right. Okay. Last time we begun an important discussion in order to really understand atomic molecular structure and interactions with electromagnetic fields. We need to think a little bit harder about the problem of rotational symmetry, which plays a very essential role in AMO physics. So, in order to do that, we needed to begin the discussion and review of the formalism of tensors. Okay? So tensors are objects that behave a certain way under a rotation. Okay? So they are mathematical objects which, in some sense, capture the behavior of objects under rotation, in this case, in 3-dimensional space. So a general rank K tensor is defined as an object which has a set of components labeled by K indices. In this case, we're talking about rotations in 3-dimensional space. So each of these indices go from 1 to 3, and each of the indices then are summed over the components of a rotation matrix. Now, one of the things that's a little bit confusing here, and it came up, Tom isn't here at the moment, but we were discussing this at the end of the class, is there are 2 vector spaces that we're dealing with. There's 3-dimensional space, the configuration space that we live in, and then Hilbert space, which is also a vector space. And in quantum mechanics, we're talking about both things. We're talking about physical observables like electric dipoles, which are vectors in 3-dimensional space, but we're also talking about the state vector, the wave function for our atom or molecule, which lives in a different vector space. And we kind of go back and forth between them, so it gets a little confusing. So try to keep that in your mind. What space are we talking about? At this point, I'm not talking about quantum mechanics at all. I'm just talking about rotations and tensors. At the moment, just a reminder, these tensors, let's just think about them as numbers, not operators. But we're going to talk in a moment, just a reminder, we're talking about tensor operators. Okay? So, we can have then a scalar, which is an object that is rank 0, therefore doesn't transform under a rotation, or a vector, which is a rank 1 tensor, which transforms as such, according to a rotation matrix. And following up on the suggestion that Ben made about how to think about these tensors by just writing out the matrices. Ben wrote up some nice notes which I posted on our website. You can download there. Let me just remind you of this. So one way of, say, forming a rank 2 tensor is by looking at the outer product between two vectors. This is the outer product in three-dimensional space. This is not the outer product in Hilbert space, necessarily, okay? So the components of this tensor are just given by the products of the components of the two vectors. And written out as a 3x3 matrix, this is that 3x3 matrix. But as we discussed last time, that 3x3 matrix can be decomposed into three other 3x3 matrices, which are the irreducible tensors. So I could break this up into a piece that is proportional to the identity matrix, which is the scalar part of this, the irreducible scalar part of this tensor, because the identity matrix goes back to itself under rotation. So this is 1/3 the trace of that matrix. There's a piece here which is an antisymmetric tensor, and you see its components are related to the components of this tensor are related to the components of the cross product sum over repeated indices here of those two vectors. So it itself has only 3 independent components specified by these 3 numbers. These are just the negatives of these numbers because it's an antisymmetric matrix. Right? So this is the negative of that, etc. And then we have a piece here which is the traceless symmetric part of that matrix. And that is an irreducible rank 2 tensor. In this case, just a classical tensor. So this business about irreducible tensors gives us a clue in terms of how we should think about tensor operators, because these objects, as we will review in a moment, are objects that kind of look like the components of spherical harmonics. And the components of spherical harmonics are objects in wave mechanics that have a definite angular momentum. So the irreducible tensor objects are like objects that have a definite angular momentum. And therefore, conservation of angular momentum will play an essential role in terms of our calculations in quantum mechanics. They also play a role in classical mechanics too. I mean, the same principles apply. In classical electromagnetic, we don't usually think about, or we often don't think about, the angular momentum in a classical electromagnetic field, but electromagnetic fields classically carry angular momentum as well. They carry energy, they carry momentum, and they carry angular momentum. But it sort of really comes to the fore in quantum mechanics because of the way in which we do our calculations. Now, before I get to that irreducible stuff, let me just say what we said last time, which is the notion of a tensor. Well, we've had first what we call the vector operator, which was a generalization of how the position operator transforms under a rotation. So the position operator transforms according to some rotation. That's to say the components, each of one of those, the x observable, the y observable, and the z observable transform under a rotation such that the new coordinates are related to the old coordinates according to a rotation matrix. And more generally, we had this expression. And then we said this is equivalent to saying that the vector operator, I should say that this rotation, of course, we know, and this is where it gets confusion. We have the three observables, x, y, and z. But x, y, and z are not numbers anymore. They're operators, which means they're matrices themselves in the representation of Hilbert space. Whereas here, you know, these coordinates were numbers. So now these themselves are matrices. And we know that these, to do it, the way in which we transform to do a rotation in quantum mechanics is through the rotation operator, which acts on Hilbert space. And that rotation operator, written here as D, it depends on the particular rotation we have, the way in which I perform that is a unitary transformation. So D is a unitary operator on Hilbert space. Which, if I had an axis angle representation of that rotation, that's one way of specifying rotation, would be equal to the rotation generated by angular momentum, if it's position, and more generally, J. If V is a vector which is more than a vector operator acting on orbital degrees of freedom, it might also act on some spin degrees of freedom. So J is kind of the generic J. J kind of has two meanings. Sometimes when we just want to say an arbitrary angular momentum operator, an operator that satisfies the commutation relations in quantum mechanics, we say J are the components of an angular momentum. This could be spin, orbit, or some combination of spin and orbit. Also, in atomic physics, sometimes J means specifically the electron's total angular momentum. When we add the orbital angular momentum to spin, we mean J. When we add a nuclear, we call it F. But J has those two different meanings here. Okay? So we say that V is a vector with respect to rotations generated by angular momentum operator J if under a rotation the three observables, which we call Vx, Vy, and Vz, or V1, V2, and V3, transform this way. Notice there are two different kinds of rotation matrices here. There's the rotation in three-dimensional space, and there's the rotation operator on Hilbert space. Be careful. Okay? And so a tensor operator, I'll be lazy, is an operator which has these components 3 to the k components, each of those components transforms like this. If we have an operator that does that, then we say that it is the components of a tensor operator. So we could write a tensor operator like this, which is the outer product now, both in Hilbert space and in three-dimensional space, whose components. So these components are operators. The components are matrices. All right? So now we said in order to deal with the fact that when we start taking outer products of different vectors or tensors, then that object isn't really, in some sense, it's not capturing its essence of its rotational properties. That really, when we take the outer product of two vectors, we don't just get a vector, we get something that we have a scalar piece, we have a vector piece, that we needed to think about these irreducible tensors. Before I begin on that, does anyone have any questions about any of this? This is complicated, I think. So lots of different things to keep in your minds. Ask questions. All right, so let me review what we talked about last time. I'm going over this again because I do think it's complicated. And if you haven't seen this before, now, you should have seen this in your graduate quantum mechanics course, which is supposedly a prerequisite for this, but I also know that it's not always covered in grand detail. The first thing that we did in order to think about irreducible tensors, it's much more convenient to deal with this in a different basis, meaning three-dimensional basis. I'm talking about Hilbert space basis, I'm talking about three-dimensional basis. We had x, y, and z, and we wrote down what are called Cartesian tensors. As I say, the components with respect to the coordinates x, y, and z. But those are not the natural objects of rotation, because x and y are not eigenstates of rotation. X rotates into y. So it was better to think about what we call the spherical basis. And that is the basis EQ, where Q is 0, plus 1, or minus 1, with such that if I rotate around the z-axis by an angle phi, acting on this vector, I get e to the minus I q phi, where E0, and I can't really remember whether this is an active rotation, not a passive rotation, and I don't remember whether this is plus or minus, so forgive me. I'll forgive you. So E0 is the z-axis, that doesn't change, and E plus or minus 1 has this overall phase out front, and then it's x plus or minus iy normalized. These three vectors are eigenstates of rotation. And when you rotate, this thing picks up a phase and this thing stays the same. This convention of minus plus, well, it goes back to the spherical harmonics. And in fact, the spherical harmonics are the angular dependence so a spherical harmonic of with L. So they're the angular dependence of Lth order polynomials in the components x sub q.
I think there's something wrong with signs at e plus
Yes,
minus
indeed.
1.
That is, thank you. Yes, indeed. X plus or minus iy are the basis vectors. Now again, we said last time that these things are orthogonal with respect to a inner product on a complex vector space. So when I expand a vector, if I want to call the qth component this, then the vector is expandable with respect to E star, which is sometimes written as minus 1 to the q, E minus q, dq, because you notice that the complex conjugate just takes q to minus q with that phase convention. So for example, if I looked at the dot product between two real vectors, v and w, which would have components vx, vy, vz, then with respect to the spherical basis, this is written as that. Q equals minus 1, 0, plus 1. So if you plugged in, VQ is, you know, for example, V0 is VZ, and Vx is minus Vx plus I Vy over 2, and plugged all that in, you would get this is equal to Vx, Wx plus Vy, Wy plus Vz, Wz, etc. Okay, try it anyway. Right. So what was I going to say? Oh yeah, I was going to talk about the spherical harmonics. So, for example, let's look. We saw that well, y00 is a scalar. So it has polynomial. The 0 is a polynomial of order 0. We looked at the 1, 0. This was equal to 1. This is minus plus over 8 pi sine theta e to the plus or minus I phi. If I got it right. And that's equal to 3 over 4 pi x plus or minus 1 over r. So the angular dependence of x1, x minus 1, and x0, right, which is z, x plus or minus iy, are the angular dependencies of the spherical harmonics. So I can think about the angular dependence of position vector with respect to the spherical basis as the spherical harmonics. More generally, for example, if I look at Z over R, for instance, if I look at X plus 1 to the power L, this is equal to X plus or minus IY times minus 1 to the minus plus, oh my goodness, this is minus 1 to the L over root 2 to the power L, which is equal to minus 1 to the L R to the L to minus 1 over root 2 front here, sine to the L of theta e to the I L phi, because X is sine theta cosine phi, Y is sine theta sine phi. So the phase dependence in phi, that's why these are the spherical bases, because they're the eigenstates of rotation around the z-axis. They have the e to the I phi dependence. This is equal to y L m equals L. Well, with some normalization factor out front. So if you're on a desert island and someone asked you, what is the L, you got to get off, Gilligan is stuck with the skipper there, what's he going to do? People of a certain generation only know what that means. But you could write down, in fact, I bet you could even write down the next one, because all I have to do is lower this. The YL with m equals L minus 1 is, I could lower this easily because the lowering operator takes this down a notch. X plus 1 goes to x0. So this polynomial, if I write this out, is this YLMs. And I can keep doing that after by the lowering operator. If you got to find those YLMs, man, this is the way to do it. Right.
I still don't understand how I get Z in there.
So that's it, yeah, that was a little fast. What I'm saying is that the lowering operator, if I apply that lowering operator, this takes this with some constant, lowers this one value. It's like taking the projection down one. So if I write out the differential operator, which exists, which you've long forgotten that there is a differential operator for L minus for orbital angular momentum, and you apply that derivatives, well, that's all it does. Now you'd have to do it out for more. If the polynomials get more complicated, now I have to, distribute them and so forth. All right. So, let's just, as an example, let's just look at the tensor, which is the outer product of R with itself. So if I write this out, now there is no irreducible vector component of this because R plus R is 0. There's no this is a symmetric tensor, so there's no antisymmetric part of this. Dij in Cartesian coordinates is xi times xj. So if I were to write out this matrix as a 3x3 matrix, I could break it up into its irreducible pieces, and it would look like this. obviously, if I just add this matrix to this, I get rid of that term, and then I just got x squared, y squared, z squared on the diagonal. And that's the diagonal terms of this matrix. And this was symmetric, and he's taking these to be numbers, so xy equals yx. I'm not thinking about the fact they don't commute because they're numbers at the moment. So if I were to write out the angular, notice there are 5 independent numbers that specify this matrix. This number, this number, this number. Since this plus this equals 0, I only have to specify 2 of those numbers. And that gives 5 components. So if I were to write this out now in terms of, right, x is r sine theta sine phi, y is r sine theta cos phi, z is r cos theta. Plug that in, I get the following. I get, stuff. 3, so these are 5 angular dependencies. This middle guy is just 1 minus the sum of these, and these are equal. These are related to the 5 components of y2n. They're not exactly equal to them, but the 5 independent components of the second order spherical harmonic, I mean, you can, Ben wrote them down for us, was very kind of him. They're somewhere, I don't have that piece of paper, but they're just related to these guys. I mean, this guy is equal to it because that's the easy one, that's the y20 term. So, the angular dependencies of which really is how the thing rotates of these tensors is intimately related to the properties of spherical harmonics. And to then see how the different, under rotation, spherical harmonics, the components of spherical harmonics rotate into one another, we can actually apply the quantum mechanics, because quantum mechanics, the eigenvectors of rotation are the spherical harmonics, so we have some wave mechanics to lean on. Okay? So, firstly, we define what I call the solid harmonics. Capital Y, L, M, as a function of a position vector is given by R to the L, the spherical harmonic Y, L, M, theta, and phi. So for example, Y, L, M equals L of X is some number times R times Z to the L, which is that normalization R to the L cos the L theta. So it's just putting in that RPL so I don't have to keep taking it out. So these are polynomials in x, y, and z, or equivalently polynomials in x0, x plus 1, and x minus 1, depending on the basis. But they're polynomials. And there are two L plus 1 different m for given L. So now what I want to know is, so these objects are what are called also irreducible tensors of rank L. What is a tensor? A tensor is an object which has components. It has, in this case, 2L plus 1 components. And it rotates in a particular way. That means the components of the rotated object are related to the components of the object that was unrotated in a defined way. How do we see how this rotates? Well, so if I define TLM, this is my irreducible rank L tensor with components M, as this solid harmonic. This is an example, but anything that transforms in the same way as this, in the same way that we just said anything that transforms like position was a tensor, anything that transforms like this collection of polynomials is an irreducible tensor. But let's define it for position first. Then TLM is this polynomial as a function of the rotated vector. That's the rotated version. We rotated this argument. Okay? So, how are we going to find, the question is, how are these components related to these components? They're not related by that SO3 matrix anymore. So the question is, how are they related? How are these polynomials related to the original polynomials? Well, we can find that by noting the following. Let's say we have some coordinate system. Here's a position vector x. Well, I'm sorry, I changed my notation. Let me call it R. Sorry. So I rotate this vector. So I can now think about quantum mechanics. In quantum mechanics, we know that this function of position space is the position representation of the angular momentum vector, eigenvector. That is to say, this is equal to this, right? If you want to write the wave function, you look at the position representation of the ket. I can think about this as R to the L times YLM as a function of beta and phi. Okay? So what is this? This is equal to the wave function with respect to the rotated position eigenvector. And the rotated position eigenvector is obtained, this is a vector on Hilbert space, is obtained by the unitary transformation, where this is whatever we had before, e to the minus I theta, or let me say some arbitrary theta. It's not the, it's whatever angle I rotate by. Okay, with that said, we can now calculate the transformation of the irreducible tensor components. T prime Lm is okay. Now, we can insert a complete set. This is only on the angular coordinates, so I can insert a complete set. Sum over L and M. Okay, where D is that operator. What is this object here? This object are the matrix elements of this object. Those matrix elements are the matrix elements of the rotation operator in quantum mechanics. In fact, we know that the rotation commutes with L squared, therefore does not change the magnitude L prime to L, only mixes the M's. So this is a matrix which has off-diagonal matrix elements in M, but no off-diagonal matrix elements in L. So it only, for a given L, there's a matrix. And these are the representations of SU2. They're the irreducible representations of SU2 with, in this case, integer L. Now we know when we go beyond position, we can have also the half integer representations, which is why we have to deal with SU2 and not SO3. When L is 1, the difference, or L is an integer, the difference between SU2 and SO3 is nothing. One is basically a double copy of the other. But this is important because now what we see here is, well, this was equal to y L prime M prime. And doing that sum, I made a mistake. Excuse me. This should be dagger. So this is this dagger, which is the star conjugate. So YL, so T prime as a function is equal to YLM of R prime is given by sum over M prime BL and M prime star. So that's why I got this backwards, excuse me. And M prime. Now when I take the transpose conjugate, it becomes n prime rather than the other way around, times y L n prime as a function. What do we see from this expression? What we see is under a rotation, the components of the solid harmonics, which are the same thing up to the overall r to the L factor as a spherical harmonics. If I rotate the coordinate, the polynomials, the spherical harmonics, are related to linear combinations of other spherical harmonics within the same L. All the different 2L plus 1 different, and this is this matrix. So the components of the irreducible tensor operator rotate into one another, where the different m values get mixed together according to the rotation matrix. The rotation matrix of quantum mechanics. Although we never did quantum mechanics yet, really here. This is all about polynomials. And we say that a arbitrary irreducible rank K tensor in classical physics, and we have them in classical physics too, is an object such that if the rotated one has components which are related to the old components according to a rank K irreducible representation of SU2, so this has two K plus 1 components. A group of 2K plus 1 objects which transforms under a rotation according to this rotation matrix, which is a 2K plus 1 by 2K plus 1 matrix, is known as an irreducible rank K tensor. Okay? A vector is a rank 1 irreducible rank K tensor as long as I write its components in the spherical basis. But if I were to write x cubed, that's a rank 1. This is a rank 1 tensor. But if I looked at the outer product between two things with two different indices, even if it's in the spherical basis, this is not an irreducible tensor because it doesn't rotate. Each one of these guys rotates according to two separate irreducible representations. But you know when you put two irreducible representations together, you don't have one irreducible representation, you have many irreducible representations. Maybe you know that. Okay, so given this, we can define irreducible tensor operators. If I were to write down the operator which says, take the polynomial, but now instead of x, y, and z, I have x hat, y hat, and z hat, and write that in terms of x plus 1 hat, x minus 1 plus hat, z hat. Write out those polynomials, those are operators, and those collection of operators transform this way. And therefore, any operator which has 2k plus 1 components which transforms according to this transformation, is known as a irreducible rank K tensor operator. God, can we have any more adjectives? Irreducible, rank K, tensor, operator. So for example, we'll see the atomic polarizability. Polarizability, how electrically polarizable an atom is classically a tensor. But in quantum mechanics, it's a tensor operator. And the irreducible components of that tensor operator I work with every day. These poor folks in the front row are stuck with them almost every day. All right. One last thing about the definition. In the same way, we said that remember when we wrote down the vector operator, we could define it. We could define a vector operator in terms of how it transforms under the unitary transformation. So this is another way to say, if I do the unitary transformation on the components, this is what I get. We can look at this in terms of an infinitesimal rotation as well, when the angle of rotation is close to 0. In which case, this unitary transformation looks like, to lowest order, a commutator. So another way of defining the tensor operator is we have this transformation, but another way to write it down is in terms of the commutation relation, which says the following. This is the infinitesimal version of this. If D is the rotation matrix generated by the angular momentum J, then the angular momentum operators have defined commutation relations with the components of the tensor. The Z component brings it back to itself up to Q. So Q is 0, they commute. If Q is +1 or -1, it gives it plus or minus that tensor back. And you see that, for example, if you look at X plus or minus commuting with LZ will be plus or minus X, because it's an eigenstate. And the raising and lowering operators commute by raising and lowering the value of Q. So this is equivalent to this. All right, lots of definitions. But I think we have the main point here, which are, there are the operators which we have a collection of operators which form the components of a tensor operator. If they transform a particular way, we say they are irreducible tensor operators. Now, why do we care? There's a lot of math, a lot of definitions. Let's think about the physics now. Of course, I'll have to do some math to do that too, but let's think about that. what we were interested in is, one of the things we were interested in is, so what we have here is rotational symmetry. What we want to get from this ultimately is what we call selection rules. That's where we're headed. What do we mean by selection rules? Well, let's recall for a moment. When we were looking at the Stark effect, back at the very beginning of the semester, we had an interaction Hamiltonian that we said was minus d dot the electric field. Remember that? And we said this was the dipole operator, which was the charge of the electron times the relative coordinate position of the electron relative to the nucleus. Okay? And so, for example, when we looked at this in hydrogen, and we looked at matrix elements, where we just say looked at this object. Between two states when we were doing perturbation theory. This is the matrix elements of that interaction with respect to whatever the eigenstates of Hamiltonian, of hydrogen were. Well, one of the things we saw here right away is we argued, for one thing, we said, if I looked at, suppose that I put in here the parity operator. Okay, this is parity. And we know that these objects, because they're proportional to spherical harmonics, and when I take r to minus r, we get minus 1 for the reason that we just discussed, minus 1 to L. That this matrix element was minus 1, this matrix element over here is equal to minus, because the parity operator, this is odd under parity, times minus 1 to the L, times minus 1 the L prime, times back to the same thing. And if these two things are equal, which they are, because this is the identity, then the only way that this matrix element could be non-zero is if the difference between L and L prime was odd, to cancel this minus sign. So we have to have states of opposite parity. In order for that matrix element to be non-zero, right? So that's an example of a selection rule. And that selection rule follows from parity symmetry. This object transformed, D or R, under certainly a parity. These states respect in some way the parity symmetry. And thus, the symmetry of the situation tells us something about how the two states are connected. In some sense, parity must be conserved. Symmetry and symmetry and conservation laws are intimately related. one way to say is that the photon carries 1 unit of parity. So now what we want to do is extend this picture to thinking about rotational symmetry. So we got this selection rule related to parity symmetry. Now we want to think about rotational symmetry. Well, let's look at this interaction Hamiltonian. If we want to think about rotational symmetry, we should look at things in the spherical basis. So we'll write down this dot product the way we did before. Using the spherical basis, right? So these objects are the components of the dipole operator in the spherical basis. Just to remind you, d0 is the z component. Z plus or minus 1 is minus plus dx plus or minus I dy over root 2, right? Which is the minus the charge of the electron and the x, relative x component of the electron that's what those things are. Now, let's consider this matrix element again. But let's stick in here a d dagger d. Okay, where d is a rotation about the z-axis for this particular example by some angle phi. Okay, let's consider that. Well, I chose that because these are eigenstates of rotation around the z-axis because they are eigenstates of the projection of angular momentum along the z-axis. So the rotation operator acting on this is e to the minus I m phi and Ln, right? Because they're eigenstates of Lz. And d, dq, d dagger is equal to e to the minus iq phi d phi. Because this is, I mean, generally we would have to write out this rotation matrix the way we just erased it. However, this is a rotation around the z-axis, which is diagonal in that basis. So each of the matrix elements is just a phase. So let's now put that together here. I get an e to the minus n phi from this guy, I e to the minus iq phi from this guy, and then I get the conjugate e to the plus I n prime phi from this guy, times the same thing back. So, what do we learn from this? Well, what we see here is, since this has to be true no matter what phi is, because this we just put in the identity, it must be the case that m prime has to equal m plus q. Because this must be equal to 1. Otherwise, 0 unless this is true. So, we have a selection rule now that says that the only non-zero matrix elements that are connected, matrix elements of the dipole operator, are those for which the magnetic sublevels change in this way. If q equals 0, m prime must equal m. If q is plus 1, then m prime has to equal m plus 1. If q is minus 1, and of course what we see here is that m prime can only change by 1 or nothing. And whether it changes by 1 or nothing depends on which component of the dipole we're looking at. So if you go back to the first week of class, or whenever the heck it was that we talked about the Stark effect, you'll remember that we looked at this along the z-axis. We put the electric field along the z-axis, in which case this was d0, or the z component. In that case, we only looked at the m's that were the same, right? That's where that came from. All right, but we want to do more than, we want to say something now about not only the m's, but the l's. Which l's are connected, and what does that tell us? So let's consider, to motivate that, let's consider this matrix element again, now written out in the position representation, okay? Something we've seen before. Let's look at this matrix element written out this is the sum over all space y, L prime, M prime, greater than phi, minus the x of q, then star here, y, L, M. Okay, so these are the two wave functions, and this is my operator in the position representation. Of course, x sub q is some number times r y q1, because we said that the components of position in the spherical basis have the angular dependence of the rank 1 irreducible tensor, which is the spherical harmonic, right? If this was z, that was cosine theta, which was y10. So now I can rewrite this in the following way. What I see is, there's some number, there's the integral over the radial coordinates of and then the integral over solid angles So we've broken up this matrix element into two pieces. One piece that depends only on the quantum numbers that have to do with the radial wave function, and something that has to do with the directions in space. This stuff has nothing to do with what direction in space I'm looking, whether I'm looking at x, y, or z direction, and something has to do with the magnitudes. Now you have for homework to look at this in detail, but let me just make a little aside over here. Because we know something about this kind of thing. This is the product of two YLMs. That's like the product representation of two angular momentum. So, aside. If I look at two kets, we know that these two kets together make up total angular momentum. And I can reuse the Lec14 expansion to write this, where I have two sums here. L goes from L1 minus L2, whatever one's bigger, to L1 plus L2, and M goes from minus L to L. So I have, this is the total angular momentum. So if I multiply two spherical harmonics together, there's some constant out front, but basically then, that constant doesn't depend on Q or M, but there is an LM, 1Q, LM, 1L. This is the addition of angular momentum. So, if I now look at the integral of this with another YLM, well, it's only going to pick off, because of the orthogonality relationship here, the term where Lm equals L prime N prime. So this is some other constant times L prime N prime 1Q Ln. This is important. It's saying that when I have this component of the dipole operator, it's like an object that has one unit of angular momentum with projection Q. So I started with a certain amount of angular momentum and projection. I then added a certain amount of angular momentum. And then I can ask, what's the probability or probability amplitude for finding this amount of angular momentum? Because I take the psi star and project out. And that projection is just the Lec14 coefficient with some constant here that has to do with normalizations and such. Well, what do we interpret from this? What we interpret from this is that this matrix element is 0 unless this Lec14 coefficient is not necessarily 0. And under what conditions is this Lec14 coefficient 0? Well, it's necessarily 0 if the triangle inequality is not satisfied. So firstly, we know that M prime is equal to M plus Q. We already got that. We did that already. But we also see that this is 0 unless L prime is equal to, or L prime is between I'm sorry. L minus 1 and L plus 1. Because we know the Clebsch-Gordon coefficients vanish unless angular momentum is added properly. So the only total angular momentum is L plus 1 or L minus 1. And that is another selection rule. So not only does L have to change by odd, it can only change by 1 unit. Parity told us that the difference between L and L prime was odd. Angular momentum tells us that if we have a dipole, it can only change by 1 unit, because the dipole is a vector. And because the dipole is a vector, it is a rank 1 tensor. And because it is a rank 1 tensor, it only has 1 unit of angular momentum. That's why the photon has 1 unit of angular momentum, and its spin is h bar. It's all about rotation symmetry. So, let me conclude by stating one last fact, and we'll pick this up next time. This example can be generalized in an important and substantial way. Notice what we have here. The matrix element of this dipole operator, which was a rank 1 irreducible tensor, can be broken up into 2 pieces. One piece that depends only on, in some sense, the magnitude of things, and another piece that has to do with the directions in space, which is a Clebsch-Gordon coefficient. We generalize this to what's known as the Wigner-Eckhart theorem, which can be proven, but I'm not going to do it. I'm just going to write it down. It just follows from the properties of irreducible representations of the rotation group, and it's a little bit nasty. It's not worth proving. Let's imagine I'm looking at the matrix elements of a rank K irreducible tensor operator. Under rotations generated by J. So for example, we have here, this is a rank 1 tensor operator under rotations generated by L. That's an example. Then this is equal to these alphas here are all other quantum numbers. Then this matrix element is equal to the following. So you write it down, and then I'll explain. What does this say? This matrix element is proportional to a Clebsch-Gordon coefficient. The only dependence on Q and the M's is here. Everything else is the leftover piece. And it has this funny double bar notation. It's called the reduced matrix element, reduced by the Clebsch-Gordon coefficient. It doesn't depend on M or M prime or Q. It only depends on the magnitude of things, J, J prime, and K. All the angular dependence, in the same way that we were able to break it up here, is separated out in a more general, if I include spin, and all of that is put into this Clebsch-Gordon coefficient. And these Clebsch-Gordon coefficients help define the selection rules. Because if this is k equals 2, if it's the quadrupole operator, well then we see how J prime can change, because I can add 2 units of angular momentum. If I have the hexadecimal, you know, whatever, I don't know, what is that, 8? But anyway, kept you long enough. Take a look at this in whatever previous text you look to remind yourself about the Wigner-Eckhart theorem, and we'll pick this up next time talking about absorption and emission and selection rules thereof. All right?